All right, hello everyone. Happy Monday. Monday, no, Wednesday. Wednesday. Great, Wednesday. All right. So I have not finished grading. These much are left. I'm gonna finish it today. So hopefully I'll give it to you after class. The solution is posted on Carmen, so you can see what you did. I posted right away after the exam. So you should know what you did. Let's not talk about that. Let's move on to today's lecture. Now, I'll just buy ice cream and make myself happy. So you have to do a class participation during the class. So if you're here, good for you. Let's get started. I just need to move to my other computer screen. All right, so since there was exam and you probably forgot whatever we talked about second order system, I'm gonna quickly review what we talked about. So this way everybody is back up to speed. So if you remember, we introduced the basic form of second order system, right? So if you are in time domain, so the one mistake in the exam was time domain and S domain was really mixed up. So these are two different universes. You can't be in both of them at the same time. It's like parallel universe, something's gonna happen to you. So if you have Y dot and you have 1 over S somewhere, that's just the clash of two universes, all right? So here, for example, this is the time domain. What are the specification of your time domain? You see time, or you see this differential equation, dot, double dot. So if you are being asked what's a differential equation, or you see time, you're in time domain. If you're asked about transfer function, pole zeros, directly, you're probably in S domain. Pole zero can also be calculated from time domain, but usually we are doing it in transfer function. But if you're asked about transfer function, then this is going to be your form in transfer function for your second order system. And you see that you have S here instead of time. So that's S domain. All right. So this is the basic form. Both of them are the basic form of your second order system. And we said that if we can put our system in basic form, we will get really important information from it. So if you have a transfer function, if you put it in basic form, you can have the equality. For example, here, you remember that omega n squared equal to some number, and then you can find omega, right? You can also go one step further and even find your sigma and omega d. And if you remember, omega n squared was equal to sigma squared plus omega d squared. So from the shape of the transfer function, you get a lot of information about system specification. This is good. That's what we want, because we can use it to analyze our system. Now, the poles of a second order system will always follow this equation. Now, depending on which type they are, they might not have all of them. For example, it highly depends on zeta. Now, if your zeta is 0, then you don't have this item. And here you have 0. So you're going to have omega and j plus minus, right? So those information we discussed, and they are available here. So go back to your lecture before this for more detail, but this is a quick reminder. Zeta tells us how our system behaves. What was zeta? Our damping ratio, right? How well our system is damping is important. We also introduced some system characteristics, percent overshoot, MP, zeta. Well, zeta, which is cosine of beta, but you'll see what beta is, I'll remind you. What is TS, what is T of P, what is T of R, which, if you remember, we looked at them in the response of our system, right? They can be calculated using our omega n and sigma. That's the beauty. So if you know your omega n and sigma, you basically know the time that your system, crucial time that your system does specific things, right? Now, if you remember this is really important. We use this plot for our controller design, like for the very beginning, for educated guesses, how we want to manipulate our system or control our system. in this plane, if this is your pole, right? The distance from the center, let's say the radius is omega n, all right? And if you remember, omega n, we just said that is the square root of sigma squared plus omega d squared, right? We also said that this angle is beta and cosine of beta is zeta. That's how we define that. Now, if you remember, if your pole gets closer to your imaginary axis, what will happen to your system? Would it damp more or less? Remember that zeta is cosine inverse of your beta. So when you get closer, so for poles near imaginary axes, right? Do we have high damping or less damping? So think about the 0 and 90, right? So you go, what happens at cosine of 90 and what happens at cosine of 0 whenever you forgot? What is cosine of 0? 1, right? So zeta is 1. What is cosine of 90? 0. So damping is 0, it's reducing. Your beta closer to your imaginary axis closer to 90, right? So as you get closer to your imaginary axis, your zeta decreases. And we know when we get closer to imaginary axis, we're gonna see oscillatory kind of response. So, and then if your zeta, so poles near real axes, it means that our zeta increases because our beta will get closer to 0. So if you remember, I used two very further example. That's just for you to remember. You don't actually have to remember this. You just need to remember what does damping mean. All right. So this fact that how our damping changes with our beta is one important factor. And the other factor is if I move this pole here, or if I bring it over here, I'm changing my omega n, right? So by changing my pole on this radius, getting it closer to the axis or going farther, I'm actually changing omega n. By changing omega n, I'm changing my my sigma and omega d as well. So let's see the effect. Yes.
I had a question on the class. Cosine beta squared zeta, what the constant inverse cosine beta squared zeta?
Oh.
It was go through one of those.
It's obviously one of them is typo.
Okay, I don't.
One of them is typo. It's the other way around.
Okay.
Beta is cosine inverse of zeta. Okay. Can't both of them be true? All right. So now let's see in an actual system from the response of a system, if we can tell what's happening. Do you see those plots? Okay, there are colors there, but I will talk about it. So you might not see from there, but if you have the lecture, it should be in front of you. Now, let's say that we want to increase omega d. We are going to keep the sigma part of it constant, and we are going to change the rest of it. So what does it mean? Increasing omega d, if you remember from just the slide before, your omega d was on your vertical axis, right? So what I'm saying is that, let's say our poles were here, was here, and we are increasing omega d as we go up, right? So we are keeping sigma constant. So this is sigma, right? Does that make sense? A pole, your pole S, is equal to sigma plus j omega d, correct? Right? So let's say sigma is constant, we are just changing the omega d part. So if I go up here, if I change it like this, I'm gonna say 1, 2, 3. I want to know how this action will impact the response of the system. So we are gonna go look at those system specification, the times, and see where omega d shows up. Then from there, we can understand what will happen to the response of our system. So omega d was equal, will appear in T of peak time was pi over omega d, right? So if I increase this, peak time is going to decrease, right? So peak time, not peak itself. So we are talking about this time. So if my first case was this, so this was T1. Now, let's say this is 2. I'm going to use color so you can see it. Case 2, case 3. Now, case 2 is this case, and case 3 is this case. Same form of the system, you're just changing the pole, one of the poles. So let's say, how is this possible? So let's say this is some transfer function. I'm going to call it f. And then you're designing a controller, right? So these two are in series. You can multiply them, right? These two blocks. So that's how you design a controller. You put the controller next to your system, and then the transfer function will be multiplication of them. So whatever is the pole of the controller becomes the pole of the overall system. So that's how we change the pole. I'm not touching the system. My DC motor is DC motor. I cannot change it, but I'm controlling it. So I can say my controller is something like 1 over s plus 2, or 1 over s plus 1, or 1 over s plus 0.5, right? So I'm changing this pole that I added to my system. That's what this means. So you're not actually changing your DC motor. You're changing the controller part of it, right? Now, the more I change, the more I increase my omega d, which is the location of my pole on imaginary axis, right? I'm gonna get a faster peak time. So my system with this controller that I just designed reaches the peak faster. So it's already a faster system, right? Makes sense? So this is one of the control action that you can do, one of the factors that you design a controller. You want your system to act faster. So you can place a pole and bring it up along your omega d, which is your imaginary axis. All right. The other thing that we can do is that increase sigma. See what happens. So I'm discussing 3 different cases, right? A pole has omega and has omega d and sigma, right? Agreed? So I'm changing one of them at a time, see what happens. So I know what happens if I change omega d. I want to see what happens if I change sigma. So I'm going to keep omega d fixed, right? So in this case, I'm going to say, hey, this at certain omega d, I'm going to change my poles, their location, sigma 1, sigma 2, sigma 3. I'm increasing my sigma values, right? So I'm going this way now. So we want to know what happens to our system. Again, we will go and see where does that sigma appear in those specifications that we had. So we remember that TS was about 4 over sigma. Now, if I increase sigma, TS will decrease. What was TS? Was settling time, right? How fast your system goes from transition to is a steady state. So like flat, right? So you want to know how fast it goes. So you would expect if sigma is farther from the axis, your system is going to be faster, to settle faster. So on here, the purple is this guy. Then the green, what is that? The green is this guy, and the blue is this guy. So this is T1, here, somewhere T2, somewhere T3. So that's second information we have. So if we put our pole farther from the axis, we are gonna get technically a faster settling time, right? Now, where to put them, that's the $1,000,000 question. We're just trying to figure out how they behave. You're just saying, what's the behavior? All right. Now, increasing omega n, which is square root of sigma and omega d, meaning that we are changing both of them at the same time, right? So do you remember how omega n would change on the S-plane? You just saw the radius, right? Yeah. So you're gonna say that if this is the line, now this time you have this guy, this guy, this guy, right? So they have different values of omega d and sigma. Sigma 1, omega d1, sigma 2, there's a negative, sigma 3, omega d2, omega d3. So increasing omega n and keeping zeta constant means that you are going on the radius and changing both of these at the same time. Now, when that happens, we're going to check where omega n appears in two places. So if when we increase omega n, we are increasing sigma and increasing our omega d, right? And we just saw that TS will decrease, TP will also decrease. So we are going to have a faster peak time and faster settling time. So this would have been our first system. Green is my second system, and blue is my third system. Is really fast. So we don't always just say, okay, let's make settling time and peak time fast, both of them. Depending on how the system behaves, you will decide. If your system is very slow, yes, you will change both of them, but you will get to a point that you only have to change one of them until you get to your sweet spot. Now, if you look here, zeta is constant, right? I'm gonna give you time to look at it. This is the last thing I'm gonna say. This was your beta, right? When I'm on the radius, I'm not changing the zeta. I'm not changing the beta. I could also be on the radius, pick one, and then get closer, so change the zeta, increase or decrease damping, right? So these are all the things you can do. You can change sigma, you can change omega d separately, you can change both of them at the same time, which is omega n, and you can also change your damping. So this means that I can place my pole anywhere in this area, and each of them will have a different impact on my system. But I can guess or predict what kind of impact it will have on the system. So when I say impact on the system, what do I mean? Impact on the response of the system in time domain that you'll see. Because these are in what domain? S domain, right? So what you're doing is you are changing things in S domain with prediction of what is going to happen in time domain. So both of these are the same universe, just work in with different physics, right? Shujian, you with me? Yes? What did I just say? Time domain versus S domain. 90% of you had problem in the exam. I'm not kidding. This is really important because if you don't get this straight, you're constantly going to mix them and everything is wrong. You can't have them, you can't have anything from here. So it's really important to understand. By looking at our S-plane, changing the pole, which is S equal to something, something, you are changing the behavior of your system. How do we see the behavior of system? Things move, right? What domain do we live in? Time domain. So we see the impact in time domain because we don't see S domain. There's another universe that has not been unlocked yet. All right. So be aware that these two are always hand in hand, it's easier to make changes here because it's just one thing. All right. So this is your class participation. I'm gonna solve this after you did, but I'm gonna give you a little bit of time to think about, and with the information you had so far, see if you can solve it. All right. So this is kind of the design problem that you will get for designing a controller. All right. So what's the order of this system? Is it first order or second order? And how do you know that? So let's see what the question is first and then jump into what I asked. So you want to find the regions in the S-plane, right? I will draw it quickly. This is the real part. I can't put on either side. This just the left half plane is negative. So we want to find a allowable region on the S-plane. For the poles of a transfer function, right, of a system that the system we can meet these requirement of if this was a requirement for the system. We don't know what the transfer function is, correct? We don't have the transfer function, but we have some requirement for that system. All right. So When we're talking about finding a allowable region in S-plane, what you can find, like what are the things that you can find in this plane? What? I think it was right, I just didn't hear. Yeah, so poles, right? Is S-plane, you find poles and zeros. So that's the only thing that you can show. So from the question, we know we are talking about poles and zeros. And we know for the poles, we just saw, we can talk about omega n, sigma, we can talk about zeta, right? Those are the things that we have access to. Do you remember the problem solving critical thinking process? So a lot of the time it comes from what question we are being asked. So I already know I'm going to find things about sigma, omega n, and zeta, and beta, something, right? Now, your system has some requirement. It says that whatever the transfer function of the system is, your T of R has to be less than 0.6 second, right? Do I have a relationship that connects TR to one of those three things that I said, omega n, omega d, or sigma? TR is 1.8 divided by omega n, yes? So this basically says that this system, this value has to be less than 0.6 seconds. So you don't know what the system is, but you know the requirement, right? So this tells me my omega n has to be greater or equal to 3, it will be radian per second, if you didn't know. And you already know, how do you show omega n on S-plane? Is the radius, right? So all the points, which are all the poles that are beyond that radius of 3 circle will meet this requirement. So I'm going to draw that. What does it mean? So let's say this is 3. If I draw a circle, well, it's not very circle, but let's say it's a circle. So omega n equal and greater. Equal means also this radius, right? Anything on this radius and beyond is acceptable. That pole has omega n greater than 3. Yes? So that's first requirement. Second requirement says MP less than 10%. So this is where you know this is a second order. Does first order system has overshoot? No. Only has to be second order. So I know from this that this is a second order system. All right. The other information I have, TS less than 3 seconds. Do I have a relationship for TS that connects it to information about poles or zeros? TS is 4 over sigma, which is 4 over zeta omega n. TS has to be less than 3 seconds. So 4 over sigma times zeta, times, I just found omega n 3 has to be less than 3. Thus, zeta has to be greater than 0.45. Now, cosine inverse of this is going to give me this is in radian, is going to be about, let's say 63 degrees. I converted to degrees, so let's not do that. Beta is 63.26. So this is in degrees. You can use radian. Degrees is easier for me to show. So this means that for all betas, all zetas greater than 0.45 is all beta less than this angle, right? So let's say this is beta. I also, because it's cosine, all the negative ones also applies, right? So anything that's in this region is gain, right? This region. So wherever these two overlap is your allowable region. This line, this line, this line. So all these blue ones, they have poles that meet system requirement. So we wanted to find that local region that the poles of the a transfer function would meet this requirements. This is a design tool. Usually when you start designing a controller, this is where you start because you want to know where's the region that you will meet a specific requirement. Why this requirement important? Because you just said TR has to be less than this much. It is important for us. All right. We can do this using MATLAB too. It's pretty cool using MATLAB, but if you understand like how it looks like here, then in MATLAB, you just ask MATLAB to plot it, but MATLAB doesn't understand it for you. You have to understand it yourself. So that's the understanding part. So I'll let you to just study this for a little bit. Then write it, submit as part of your cost participation. If you submitted already, you're good. Yes. The angle?
Or it's not the angle, but like all around the
Tell me the color. Okay.
the rays of the sun.
Yeah. So the rays of the sun was omega n.
Yeah.
So your omega n, we found omega n from this characteristic, right? I'm gonna go back to this. So this comes from here. So omega n was this radius. So if you want omega n to be greater than some number, then you have to keep going that way. So that is like 3 radian per second. And anything greater than that is acceptable. So did I answer your question? I'm not sure if I answered it. Okay. So the question asking what is the allowable region? What is the acceptable region for this transfer function? So if you have omega n, you have zeta, and if you have sigma, can you write the transfer function for me? Yes, you can. Write a transfer function if you do some media reference function. Yes, yes. So first order system, their characteristic, they look like either growth or decay, right? There is no overshoot. Here we have percent overshoot. So I can simply say this is definitely not a first order. So there should be an element of second order in this, so I'm good. Now, if you try to write a transfer function, you have to ask me a question. Okay. Well, the poles you should know. You have all the elements. Oh my God. Do you remember the basic form? Is omega n squared over s squared plus zeta omega n s plus omega n squared, right? So that's a basic form. That's in the case that you don't have any zero in your system, right? So if that's such a case, you can say assuming 0s equals 0, like there's no 0 in the system. So it's just like a gain, k over or 1 over whatever. So second order system without any 0. That is this. So you should be able to write a transfer function. Yeah. No. Just Wednesday. No password. Create your own password. Be creative and polite. All right. So first order system, this is just a review. I just talked about it. So you either have a decay or growth because it's a first order system. We know y of t is e to the power of negative a times e to the power of negative at, something like that, right? So it's either growth or decay. You have some system and specification. The most important one is tau, right? So if you remember the basic form, so this we wrote like tau s plus 1, right? What's the very important element in the basic form of first order? What should match for sure? For this to be the basic form? If you don't remember, it's okay. Here, this has to be 1. If it wasn't, put in the 4. Then if that's 1, whatever is here is tau. Now tau is 1 over sigma. Sigma is the real part of your pole. You can find TS and, well, there's no MP, and TR from these two equations. So these two are new information, but really don't need them because the only thing important is tau and whenever it reaches steady state. Both of these responses that I showed you, they are used for designing controller. So ask any control engineer, that's where they start. But this is all guesswork. Once you define the controller, you have to run your code or measure your system to determine what is the actual TR and TS. They might be slightly different from these equations because all of these are approximation. All right. So when you get there, you will have to actually run your system to find those values. Now, this is a very good and useful graph because this is S-plane and I'm showing all combination or possibilities of first or second order system. All right, so let's see. Is this a second order or first order system? So first order, we just saw they can only be like this, right? So let's identify all the first orders. First. So on your right half plane, you have unstable region, right? Anything that falls on this region, right half plane is unstable. So this here unstable, this is unstable. Both are going to infinity, so obviously unstable. But you see that their respective poles are on the left-hand side. So identified all the first order system, these are decaying, obviously they are stable. So this is your stable region. Now, this imaginary axis itself, it's not, we call them bounded. It's unstable, but it's bounded. So you know there is a maximum minimum that your system goes in between. So that's the specific case. You don't have any damping on imaginary axis, and you can tell. This is not being damped, it's just going up and down. So it just has the frequency part of it. Anything on the left side is a stable. So this is a second order, this is a second order. This will eventually damp, but very slow. This one, sorry, this isn't damp. This one is here. These two are both of them on. So we call them, yeah, let's call them bounded until we get to stability. What is this? And this is his pole. Kevin. It is what? No, I want to know if you can guess the transfer function of this. Step function. So step, if you forgot, what's the pole? 0, right? 1 over s. 1 over s is transfer function of a step function. So all of these are transfer functions or functions, right? Step function is an input. Like you can't say that there is a system that's a step function. We created, we generated it. But hey, my laptop has a transfer function, right? When it acts normally, it is in the left-hand plane, and then sometimes it goes to right-hand plane and then unstable. Not a good example, but you understand what I'm saying. When you see the blue line, blue screen, that's unstable. So this is very good for yourself to understand. If you look at the response of the system, if it's a stable or unstable, just see what does it look like. And you can get a lot of information just by looking at it. Good? Ready for another example? No? Why? Exam fatigue. How about us grading it? Huh? How many exams did you have this week? It's Wednesday. Okay, I'll leave this for Friday. Let's talk about it. So far, okay. Well, we're going to talk about control. I'm not going to let you go. But I will finish this on Friday because actually this one and next is like really important in designing controller, and I don't want to give to your tired brain. For first order and second order system, what are the things you learn from memory? Don't look at anything, just call them out. The basic forms of which one? First order and second order. So let's say, what do we learn from the basic forms? Why do we put them in the basic? Sam?
Well, second order, what am I right?
The system is a specification, right? Those are, by the way, your design specification. So you go get a job at a company, you design controllers. That's literally what you do. Oh, this using this, we're actually gonna solve a DC motor controller. Oh, this is a DC motor, this is a transfer function. Ah, this doesn't behave, I need to do this because let's say this was a robotic arm. What is a robotic arm? A piece of metal and a motor. How do you control it? Control that motor. So everything comes down to actuators, right? Now your actuator is either linear actuator or rotor. Linear actuator, like a DC motor, you have theta as displacement. You have to control theta and theta dot, position and velocity. If it's linear actuator, think about like the doors that like you move horizontally. I don't know what it's called. Let's say you enter somewhere and the door opens. Yeah, the sliding door. Thank you. My brain is right. Sliding doors, right? So how does that system work? Someone tell me. There's this sliding door in front of me. I'm getting close. It opens and I go through. How does the system work? Nothing spins in the circle. Talk like a control engineer. So first, when I get close, how does it know I'm there? There's a sensor, right? A proximity sensor. It has now the proximity sensor could be IR, right? So let's say sends IR signal, like, hey, someone short came in, let's open the door for her. So that sends a signal to the microcontroller, right? That hey, someone is here. Then microcontroller asks, so what I do? Ah, I have linear actuator. I'm gonna move these doors, right? So send a signal to the linear actuator on. Start moving. But they're not gonna just move forever because there's a limit. So it's like go for this many time or depend on how it works, PWM or angles. So it will open and then I go through. So either has timing control that after 5 seconds close it, or still sending the signal on the other side. See if this person is farther than this many meters, right? Then close back. That open close is controlled by you, control engineers, right? It's not too fast or not too slow. How do we define too fast or too slow? Did you learn something today about it? The time, TS, T settling time, right? So T peak is like, oh, the motor gets to the rev, right? And then settle, so it opens. And I go, and then, okay, get back for it. And so that part, you write that controller. Yes. Like that. You know what's unstable? Have you been in that scenario? It does not like, it's kind of like either broken or something happened, keeps closing and opening, you cannot use it. That is the unstable part, right? So it does not reach to steady state. So it's the imaginary axis keeps opening, closing, go back and forth. So something, some signal there is not getting to where it should. So even this system is very smart, very simple, but has a sensor, an actuator, and a controller. So as control engineer, you will be able to work with this and design the system. You decide how fast I want this door to open. So let's say you are in an air-conditioned room, so you probably want to close that door very quick. If you're not, you can just be slow, okay, we'll close eventually, right? So you decide that. So all the things we learn here, it looks, it's all theory, is on the paper, it's just in the book, but it's really not. you will use all of this if you work as control engineer. Now, control engineer in robotic, industrial robotic, you don't have to be just in control system. You can be in automotive industry. You can be in watering garden, whatever, what is that they do? Like automation, like automating water gardening, whatever. So something has to open a valve, send this much water out, sprinkle with this angle and close. All of that is control. Control is everywhere. And it all boils down to omega n, omega d, and sigma and zeta. I'm not kidding. Because they're all about time. Now, everything else, all the tools are the fancy way of just making this process faster. So instead of me doing all by hand forever, it's like, hey, MATLAB, use this toolbox, fancy toolbox, do all of this and tell me how things work. But the basics are all the same. So I want you, when you're here, if you really like, this is an elective class. So you either liked me, took this course, to be honest with you, or you like control. Some of you wanted to graduate. So I'm not talking to those of you that you don't care, you're just here to graduate. The rest of you, you're here to learn something. So be here with excitement. Okay, be ready. Yeah, because these are useful. This is probably could be one of the useful classes you take in Ohio State because you don't have to take it. That's why it is designed to be fun. So I can teach you just this and stuff, and the rest of the semester just talk about it. No one tells me why. Because, you know, it's elective. You don't have to take anything after this. So how are you on the grading part? Okay, I'll talk 5 more minutes. I'm going to give you your papers back. All right, so what else did you learn so far in this class? I'm not leaving you going out. Drew. Okay, put the mask on your nose. Thank you. If you don't do that, I'm going to take it off. What did you learn in this class?
Block reduction.
Block reduction. Why is that useful? I actually like it that you said. Why is it useful?
All the system.
So, why is block reduction good? You buy a DC motor, right? You have to do things to it. Thus, you need a controller. You design your controller as like s plus 1 over s squared plus 5s plus 1. Then you buy a sensor, and it has some sensor like transfer function h, whatever, right? This is your system. You wired it. Literally, that's a block diagram. And then you want to know like how your system behaves. Like if you just give it 3 volts, what is going to happen? 5 volts. These are like a step inputs, right? Just constant 5 volt. What does it do? If you want to analyze this, what is your next step? You reduce it to something that looks like this. This is what you would put in MATLAB if you're having any programming, anything, or if you're solving by hand, that's what, because that tells you like what kind of system you have. So if you when you get a complicated system, you can break it into simpler blocks. So it is a very good skill to have. And in your exam, you saw a block diagram of a differential equation, which usually we have the differential equation. We go from differential equation to block diagram. You should be able also to do the other way around. So we're very comfortable between these, all of these. What else? What else did you learn in this class? Seth. Okay, who is ready? No, you're in the top. Yes. Using MATLAB, that is useful. You will use that on Friday also. Yes. So why is that? Why do you think that's useful? Why not use it? I don't know.
So I came up in like some machine class, like awesome changing.
So when you use a steady state space, right?
Yeah.
What does that represent? It's your transfer function is in time, it's not a transfer function, it's a representation in time domain. But sometimes understanding something in time domain is easy. So we represent it as those matrices that you all take. Now, if we didn't want specifically, we didn't care about time domain, we could work in estimate, right? And then we'll have the transfer function stuff. All right.
So, I do have like 5 people that we did this for a minute, but.
So this is A to H over here.
First name or last name?
Last. So far, J to W here, we have 5 more W.
Pause this recording, that's just forever.